Awesome. Well, good morning, everyone. And we'll kind of get right into this. I believe there's some time at the end for questions. Um, Thank you very much to Holden for having me in today. Again, name is Greg Allen, application engineer. What we're going to go through and review today is fan curves. Fan curves, such a simple topic, most would think. But really, when you kind of dig into it, it becomes a living beast. And this is an opportunity for me to kind of show everyone here how I see, kind of through the eyes of an application engineer at Greenheck, how we would see a fan curve. We've added some information to this slide deck towards the end, kind of expanded on some system effect and fan energy index, which is becoming kind of a common thing now to have to be aware of. So, without further ado, let's just kind of jump into this. And I think I'd be wrong if I didn't start a good fan curve class by talking about um, fan laws, right? Fan laws, the way I see fan laws, man, this is the math behind a lot of your fan curves, right? So the fan curves are going to be our graphical, our language that we can talk back and forth and be on the same page and understand each other when we're trying to convey the performance point chosen versus its capability at different points of operation, right? But all this really boils down to in the beginning just understanding the fan laws, also known as the affinity laws. And of course, we have law number one. Law number one right here, simple equation. And this tells me that as my RPM changes, my CFM is going to change 1 to 1. I mean, I call this the happy fan law, right? I mean, I need 10% more CFM. Great. 10% more RPM. Done. Right. But then we move into the second fan law, right? And the second fan law relates how that system resistance is going to react to that change in RPM, right? So as I change RPM, my static pressure is going to change to the square. Okay, I call this the uncomfortable fan law because, 10% more volume and need 10% more RPM, we're good to go. But that system's going to experience 21% more static pressure, right? So when you ordered this for, a quarter inch of static pressure, well, now we have to add 21% to that. And then we get into our third fan law, which I refer to as the expensive fan law. And this says, as I change RPM, the brake horsepower, the power needed to move that air is going to change by the cube, right? So that simple 10% more CFM, yeah, requires 33% more horsepower to move that air. Right. So these laws are tried and true, great information, especially off the cuff when you're looking at you know minor or major changes using existing equipment. Simple rules you can go through and say, okay, if I need 10% more volume out of this air mover, I can expect to need 33% more horsepower. Look at your horsepower of what's in that fan and do I have it available? All right. So one more thing I like to throw into this. I mean, some people will say that the fan laws are discouraging. 33% more horsepower. Ouch, that's a new motor for me. But there's the encouraging side of this as well. There's the light side of the force, you might say. And that's if I turn a fan down, right? If I simply turn a fan down 10%, you just see the savings, the power savings, the electrical savings, the less static pressure, the less noise. See all those savings rack up very quickly just by a simple turn down. So when we look at design philosophies and air movement, moving 1 RPM all day, every day, I mean, that we've done that for years. But a on demand or a variable volume system can really make a difference in sound, vibration, and cost for monthly upkeep. All right, so get off that soapbox and I'll keep moving on. All right, this class is all about fan curves. So let's talk about fan curves. Right on the screen right here, this is a traditional fan curve. This is the medium that I'm going to use to take really cool data. I mean, this is information that has gone through really nice test equipment, real data numbers pulled, and this is my ability to show off to you, whatever fan you selected, this is how it's going to react in different environments, right? So right off the bat, let's just kind of break out the different pieces of this fan curve. We're going to start basic and we're going to build up from there. Number one, across that bottom X axis, right? The horizontal. This is volumetric flow, right? So 300, 3000, whatever the air movement is going across the bottom, that's my air movement. Now on the left vertical axis, this is where I'm going to compare that air movement against the system resistance or the static pressure in the system, right? So now I have an XY graph. Now there's some more information on the screen. We kind of got to point out on that right-hand side, that secondary axis, this is where I'm going to let you see the brake horsepower, the power consumed to move that amount of air with that fan against that system resistance, right? I'm starting to pull more information together. All right, so let's go to the middle of the screen now, and we're gonna kind of look at the different lines and blits and bobs that appear. Number one is this red curve, right? That's the fan curve. That is the recorded performance of how that fan is going to move air at a specific constant RPM, right? So right out of the bat, kind of that top left area, you can see that my example, this fan is running 1448 fan RPM. Okay, quick stop here for definition. FRPM versus RPM. Typically, manufacturers are going to say RPM when they're talking about motor revolutions per minute, right? That's the speed of the motor. When you see fan RPM, this includes like belt drive systems where there's a mechanical, reduction in speed. So in this scenario, the motor might be going 1725 RPM. Your impeller is moving 1448 due to that ratio, that relationship of sheaves and pulleys. All right, so I have my red curve, and as you can see, static pressure versus volume of air, it's an inverse relationship, right? As I move more air, I have to move it against less static pressure. As static pressure in a system starts going up, I move less volume, right? So that relationship holds on that curve. Now, the next curve that I throw on here, that's that blue dashed line. And then that's our system curve, our system resistance. When you go into your fan software selection um, program, right? And you put in, hey, I want to move 1200 CFM against 2 inches of system resistance. That 2 inches literally defines the shape of that blue curve, right? So as you change, or if you change your system resistance, your static pressure, that blue line will move. And I have a slide coming up here, kind of really emphasize that. But the spot where the system resistance line and the fan curve intersect, where they cross each other, you'll see I have a little black circle right there. That's called our operating point. Where they intersect, that's where that fan at that RPM is going to perform, right? So in a system that has 2 inches of static pressure, this fan at 1448 RPM will move 1200 CFM. So that's kind of the goal right here, right? You're going to go out, you're going to try to select a air mover that's going to meet the requirements of your building. And that's our requirement. So great, this fan's going to move what I need. Now, there's a couple more things on this curve I kind of want to point out. That black dash line, that's my brake horsepower, right? Now, the brake horsepower is showing at that point of operation. This is how much measured horsepower it takes to move that air against that resistance. Again, this all goes back to that AMCA, the Air Movement Control Association, that big brother that really defined for us manufacturers how to test equipment, the equipment to test it on, how to display data. All of that's pulled in here. But one of the things I have to record was the amount of power consumed at each of these points. And I'd take so many data points that I'd make a nice smooth curve, even better. Now, how to read that brake horsepower curve, this is a little different. I mean, when you look at your volume, you take your operating point, you go straight down. That's the number you're moving for volume. Straight across, that's your system resistance. Well, for brake horsepower, you got to read this curve just slightly differently. What I got to do is I got to take a line from my operating point and then draw it down or up wherever that brake horsepower curve is fit onto this graph until I hit that curve. And then I need to pull across my secondary axes. In this scenario, I'm moving about 0.85 brake horsepower to move that 1200 CFM against 2 inches of static pressure. All right, so this really is kind of the crux, the main part of fan curves, right? So this is the main data we need to look at. Um, how these different lines are developed, they're recorded using test methods, how that information is posted and shared with you, the user. So this is kind of the most of it. Now, from here, we're going to start going into the fan curve a little differently, talking about different areas. You'll see. First thing I kind of want to point out is the do not operate zone, right? The don't go in there zone, right? This is an area of a fan's capabilities, right? That this fan will have poor performance, right? Even more than poor performance, it can have destructive performance. All manufacturers of air movers are going to give guidance and say, do not pick or operate a fan in this region. You can get effects such as surge, stall, hunting, you know, all of these different bad things can happen. Some of them go from annoying or just not quite the performance you expect to actually breaking down the fan, wearing the bearings out. A great sound effect. Not if you're in the building, but cool from an engineer's point of view. So the do not operate zone, let's kind of zoom in on here and kind of look at one specific scenario, right? And that's hunting, right? Hunting is the phenomenon where a fan can operate at more than one static pressure, but at one static pressure, but two different CFMs. So let me throw a line in on here. And as you can see here, I can actually move, 100 CFM if I cross at just about almost 2.2 inches of static pressure. But I also cross the fan curve at 700 CFM, right? So I got these two different points of operation. If I actually have 2.18 inches of static pressure, which volume is this fan going to actually move? Is it going to move 100 CFM or is it going to move 700? The reality is the fan doesn't know and neither do I. It's going to try to do both. Unfortunately, that doesn't move. It's gonna move 800 CFM. That's not additive. What it's gonna do is called hunting, right? It's gonna load up. It's gonna move that 700 CFM, and then all of a sudden it's gonna download and move 100, and then it's gonna build back up to 700, and then download again. It's gonna hunt back and forth across that fan curve. Now, to put this in kind of a point of view that I can relate to. Imagine going down the highway. It's a nice, beautiful day. Sun's shining. we're in a 5-speed stick shift and you're doing 70 miles an hour in fifth gear. It's gorgeous. And then you decide that second gear is really the place to be. So you drop a couple of gears, you pop the clutch out, and then you move it back to fifth gear, and then back to second gear, and then back to fifth gear. How long do you think that car is going to last you treating the transmission in that manner? The reality is the car is going to probably last as long as the fan doing the same thing. So that is called hunting. um, Kind of some of the other things I brought up, like stall. Stall occurs when the CFM being moved is too low compared to the tack angle of the impeller. Thus, you lose the ability to push air forward. You stall. Commonly, this is caused by having a fan that is massively too large for the small airflow that you're actually trying to move. The fan in this scenario tends to be noisier, sometimes even sounds like hammering. If you can, I think of my house when you turn the heat to a certain point and you hear that water hammer. That's not good either. But that can happen with air. You get aerodynamic shocks, and this can cause damage to the fan, even fatiguing the metal components. And the last part there is surge. So surge requires a positive slope fan curve. So basically, you're operating to the left of the peak pressure, and we're going to hit peak pressure in a moment. A system in surge is like kind of an oscillator, right? So the energy imparted to the air alternates between creating kinetic energy and potential energy. The positive slope on the fan curve allows the large amplification of this oscillation. In extreme conditions, um, the air can actually temporarily belch or blow back through the impeller, right? Especially if you have, like, say, a propeller, and this can happen to centrifugal wheels as well. But you're pushing air one way, you're moving too little air, and you start building that pressure in the backside of the fan. It can actually push the air backwards. Yes, it can be mechanically bad, but depending on what's in that airstream that you're trying to evacuate from the space, that could be even worse, right? What am I reintroducing into the space I just tried to evacuate? All right, a couple more types of fan curves that I want to make sure everybody's introduced to. Here's an RPM family fan curve. And this is basically saying, okay, we have our blue system resistance line, and anywhere I cross the RPM line, the fan curve line, that's my point of operation. This type of fan curve can be read as, well, if I speed my fan up from 1448 fan RPM up to 1687, now that new intersection point will be my performance point. Again, if you kind of think back to where we started, the math behind the fan curves, this is literally my first and second fan laws shown graphically, right? At different RPMs, as I change RPM, my CFM will change 1-to-1. And the curve of that system resistance line, that blue line, that's going to be an exponential curve because it changes to the square. All right. All right. So, quick reality check here, folks. We're going to put your brains to the test after getting some good information. I have my scenario here where I have an upblast fan, right? And I picked this fan perfectly, right? I am moving 1200 CFM against 2 inches of static pressure. My operating point is right there. Now, we go in, we install the system. Ductwork has a couple of extra elbows. I had to go around, the life safety and the plumbing piping that beat them onto the job. So now the ductwork, instead of going that beautiful route that was designed for it, it's going to have to shift a little bit. Not a huge deal, but each of those elbows, those changes, are going to introduce more system resistance for this fan to overcome. So all of a sudden, I've got a 1/4 inch of extra static pressure that I wasn't accounting for in design. What does that look like on a fan curve? Right? So this class is about fan curves. Well, if I change that blue system resistance line and add a 1/4 inch, all of a sudden that curve starts pulling up, right? It starts curving up. And now I have a new operating point, right? I'm not moving 1200 CFM anymore. I'm moving closer to 1100 CFM because I have a little more static pressure. But in the end, I also need to move the amount of air that that building needs. So I need to move my RPM line, my fan curve line up so that the intersection between my static pressure and my fan curve happen at 1200 CFM. The only way to get there from here is to speed it up. And in this scenario, that I grabbed, it takes this fan from 1448 fan RPM. I got to bump it up to 1525. Right. So to overcome a little extra static pressure that was in the as built system, I needed to actually speed this fan up, almost 100 RPM. That's going to take more horsepower, right? Fan curves, fan laws, excuse me. It's going to take more horsepower. It's going to cost me more every month to move that air. There's more system resistance. There's more and faster moving air through that ductwork, so I'm going to hear it better. Now we have to balance. We have to move the right amounts of air. I'm just kind of cluing everybody in on the unintended consequences of this scenario happening to you. Yeah, you may all of a sudden have enough sound change where people see it, hear it, um, and sometimes complain about it. All right, same scenario. Let's say I overshot. I padded my numbers. I made sure 2 inches is what I calculated, but um, there's actually only say 1.75 inches, right? So if you have less static pressure, that curve starts laying down, right? And then I've got a new impact point. So now I got to slow the fan down so that my curves, once again, let's see if I can do it. I got to slow that fan curve down, change my RPM so that again, I'm crossing at 1200. And in this scenario, I'm at 1365 to hit that golden point of moving 1200 CFM. Now, this entire exercise that we just walked through here of this example was really about having you see a fan curve the way I see it. Everybody sees static lines and when they look at these beautiful pieces. What I see is what could be. Add a 1/4 or 1/2 inch of static pressure, or remove that. In my brain, I'm seeing, those fan curves pull up and push down to different points of operation. So hopefully I can kind of let everybody here see a little bit of fan curves how I see them, kind of a living tool. I'm going to go into some other curves. I'm trying to keep myself moving here with the class, so there is time at the end. If there's any questions, I believe Tracy's taking those questions. Correct me if I'm wrong.
Yeah, you're
But
good. You're
go
good.
ahead.
You're
Awesome.
good. Keep on going.
All right. So what I have on the screen right now is just a derivation of a fan curve, right? This is a fan curve plus a little extra information. In my mind as an engineer, this is my absolute favorite fan curve. This is the one I go back to time and time again because it has all the basic information I've provided in this class, right? The red curve is my fan curve. The blue curve is my system resistance. I got an operating point. I got brake horsepower. I got all of that. This one adds just a little bit more, right? So as we're in um, specifically direct drive fans, and also belt drive as well. Say you have a belt drive fan on a VFD, or you have a direct drive fan with a VFD, or maybe you're using one of those really cool EC motors that have this huge range to play with, right? Now all of a sudden you have a system that can hit different operating points depending on which RPM you pick. That's where this fan curve comes in, right? This is telling me that bottom purple line where it states 483 fan RPM. It's trying to tell me if you turn this all the way down, That's your bottom end air movement, right? We're talking about 400 CFM. Now, the green line that's just above the red line, that is that fan as picked with that motor, its max capability, right? So this fan has a, let's call it a 1 horsepower motor. Um, we run out of horsepower at 1530 fan RPM, right? And if you want to go any faster than that, you needed a bigger motor. The nice thing here is at 1530, again, I cross wherever the system resistance and the max condition fan curve cross. I can draw that down and say, okay, this fan I just procured can move 400 up to, let's call it 1350 CFM. That's my box, my range I can play within. That is gold to have for knowledge as you're picking and specifying air movers, right? Maybe you're in a situation where phase one, I need to move, 600 CFM, but for phase two, I need to move 1200 or 1300, right? Am I procuring different fans for each phase? Or can I order one fan that has the legs to overcome multiple phases of this project? Or maybe I have a situation where, normal operation versus alarm or emergency operation. Say you've got a mechanical garage, a city garage, right? From 8 to 5, I need to move, 600 CFM. I'm making up numbers, folks, but I need to move 600 CFM just because people are in the bays. Now, I have a carbon monoxide detector that's going to send this exhaust fan to max air movement if it is in alarm state, right? If someone pulls a truck in, that's truck's still running, I got carbon monoxide everywhere, and I got people working on them, I need to bump up, move max speed. This type of curve um, gives you that information of what's my min to my max. It also helps you make a choice. This is this fan picked at 1 horsepower. There's one more curve on here, and that's that top purple line. That top purple line is that fan's max capability or construction maximum, where we do not encourage or allow that fan to be operated any faster than that, right? That might represent the biggest motor available for that fan. That might represent a very mechanical construction where I don't want the impeller spinning any faster. So instead of maybe ordering this fan with the 1 horsepower, my green line is at 1530. Maybe I bump this up to a 2 horsepower. All of a sudden, that green line moves up until that green line and the purple line become one, right? You have the biggest motor available on that fan size. This puts you in the driver's seat of picking the best fan. So I've got a couple arrows here. There's my fan curve. My max fan as selected, right? That's what the horsepower that's originally said. You got my min, and I've got my max curve for construction of that fan. So you can see why I love this fan curve, right? It allows me, when I'm specifying and selecting fans, to really be in the driver's seat of overall capability. What's its range? And that could be for today or for the future. One more thing I want to point out here, and that's some simple math. Up in the top right, I took the operating fan RPM, that 1448, and divided it by where the green line is, the 1530 fan RPM, right? What I want to do is in my own head, understand I am picking this fan at this point, I'm specifying it. I want to know like how much of max am I at? So simple math, right? 1448 divided by 1530 equals 0.95. That means I am knowingly picking this fan at 95% of its capability. That might be awesome, right? That's great information to have. And that means I probably have the smallest fan possible to move this air because I'm almost maxed out in that fan's capability. I have 5% to turn up. Back to those fan laws, right? When did I, remember the 10% change of RPM, 10% change of CFM? Well, This is telling me I've got 5%. Before I run out of horsepower, um, I am knowingly kind of specifying this fan. And if that number is not a good one for me, let's say I'm going into a construction where it is very likely my ductwork is going to move multiple times from design to reality, right? And there's a chance that my static pressure is going to do this, or there's a little bit of system effect here. Is 95% a good bet to make sure that this project goes without a hitch, as much as possible, and moves the air I need it to move? If 5% turn up is not a happy place, maybe you like 80%, right? I want 20% turn up, 60% turn down. I want to be in that range. Well, you're in the driver's seat now. You want to bump that motor horsepower up so that you have that higher buffer at the top end. Or you may choose to just pick a different fan where the operating condition gives you more favorable turn up, turn down relationship. And actually, that's my next curve is I can throw different fans, different scenarios onto the same curve to see how they would operate. And that's right here. I'm just comparing a 16-inch wheel versus a 24-inch wheel versus a 14-inch wheel, right? Where are they going to fall? Lay them on top of each other. So as the engineer, I can make the best choice. Now, in our scenario, we're dealing with that red line, and that's a pretty good looking fan curve. I'm hitting it in a desirable spot of its operation. So again, just another good fan curve that's at your fingertips for you to review. Now, when I said, is this fan operating at a good point? Boy, that opens up the doors for, well, what's a good point of operation for a fan, right? What's a good fan selection versus a bad fan selection? Some of that turns into the needs of your customers and clients. Um, some of it is what's available in the industry for that type of air movement. Some of it turns into cost. A larger fan typically costs more than a smaller fan. A larger fan's typically quieter than a smaller fan. So you're weighing as an engineer all these different attributes and trying to pick the right one that's going to, work on the day that the inspector is there and you're signing off your T&B, um, but is doing you're a great steward of the dollars for the end client, right? It's always about a balance. But looking at these fan curves, I can get a little bit more information, right? Let's look at static efficiency, right? Static efficiency is calculated using only static pressure. And this is important because the fan you've selected, I can look at, was this the right or the wrong fan, um, in its operation. So here, this curve I'm showing you, all of a sudden there's that small black dotted curve. And what it's saying is that this is the static efficiency curve. If you're operating towards the top of that curve, that black dotted curve, you're in the most efficient spot that fan will ever operate in. If you're towards the ends where it drops off, you're operating in a point the fan's going to move the air. It's just less efficient at doing it. Let me kind of show this another way. Let me circle a range here. That range that within the blue circle, this represents that top, let's call it 15% of the static efficiency curve, right? So if our system resistance line ends up crossing our 1448 fan RPM curve anywhere inside that blue circle, I am really at the top end of this fan's performance, its efficiency, its capabilities. Even though if I have a bunch more or less static pressure, that curve could go all the way outside of that blue bubble, and I could be operating in a less efficient. The fan will move it, just not as efficiently. When I say efficient, I'm going to probably say it 10 more times here. This is where our world is going. Whether you're talking about, local and state codes and requirements for efficiency, or we're talking about federal programs, Department of Energy. We're going to hit that a little bit harder here in a second, but I want you to remember this blue circle because this is going to show up again. All right. So static efficiency, that was looking at efficiency with only static pressure represented. There's also a total efficiency. And total efficiency is a summation of both static pressure, the system resistance, and the outlet velocity pressure, right? So now I'm taking both into account. Um, for this fan, you notice the curve actually didn't really change because the fan I'm using as an example is a rooftop exhaust fan, right? There's not a bunch of ductwork after the fan. So no big difference. If you have an inline fan, these two curves will show differently. And you can pick the right one to show you the information and the best points of operation with the fan you picked. All right. So just looking at total efficiency here, what I'm trying to circle in red is that peak point, right? This is that one point where this fan is as efficient as it'll ever be, right? And this is actually showing, 52% efficiency on this curve, right? That's the top or peak point of operation. If you can run into that point exactly, perfect. But where I want to kind of deviate here for just a moment is let's say I'm not operating. I can go back a couple of slides here. Let's go back to that blue curve. Let's say the fan I picked, it fits perfect. It's the right cost. It's the right look, but it doesn't cross the fan curve in that blue circle, right? It's outside of it. What are my choices, right? I suppose I could add some extra, static pressure in the system and pull that curve up. Um, but the reality is I'm likely looking at either taking that fan and speeding it up or slowing it down, or I'm looking at a different size of the same type of fan. And as you change sizes, like the one I'm using as an example here is a 24-inch centrifugal wheel. If I bump that to a 30-inch centrifugal wheel, all of a sudden you'll find that that blue system resistance line is going through the closer to that peak operation point, that most efficient point. So if you're ever in a spot where the fan you want, you look at it and it's not exactly the most efficient, maybe look at bumping it up a size or two so that you're operating in the fan curve at a more efficient point of operation. And that's actually kind of a good thing to bring up because we're going to bounce off of fan curves for just a hair and talk about fan energy index, um, FEI, right? So, according to the Department of Energy, industrial and commercial fans represent about 2.5% of total US energy consumption. Okay. 2.5% may seem small, but when that's 2.5% of total is just used by fans, that's a lot of energy. So if you're trying to reduce, the usage of power, be a better steward of that uh, energy, one of the places that are going to be looked at quickest is likely to be fans. Are people picking fans in an efficient spot of operation, or are they not? And there will likely be some regulation that's going to force you into selecting a better fan. Well, here's a tip of that right for you. Let me just kind of break out what FEI is quick. So FEI is a wire to air look at a fan's efficiency. I mean, literally on the left hand side, power in, on the right hand side, fan power out, right? This is beautifully, way to look at efficiency. And what we're going to do is we're going to compare the fan you picked at the performance point that you picked and compare it to a baseline calculation, a baseline fan. And that relationship, that ratio, is going to give you a single number FEI value. What goes into wire to air, and just kind of circle this quick. motor losses, drive losses, bearing losses, aerodynamic losses. It looks at all of it because it's wire to air. So I'm actually a big proponent of the FEI number. I think it's a great comparison of, let's say you're looking at two different fans or two different size fans. Um, it's a great one number value where if you're at an FEI of 1.0, meaning you're pretty well average or good, that's a good spot to be. Anything above one is great. Anything below one, you might want to relook at your selection because you're operating in that less efficient zone. So actually, let's go back to a fan curve and kind of overlay here. I've got my fan curve. I've got my brake horsepower shown, my do not operate zone in red. Let's throw a couple things on here. Number one, operating in a low efficiency point of that fan's operation or capability, right? So this is going to be low efficiency and higher sound. Then I've got that, what was a blue circle. Now I've got the operation of this fan in a higher efficiency and lower sound because it's in a more efficient spot of its own operation. Now here's where we're going to bring in FEI, fan energy index. I'm going to lay that over the top. What I have circled here is everywhere that this fan has an FEI of 1.0 or greater. If it's outside of that red circle, it has less than a 1.0 or less than the baseline fan for efficiency. So what you're kind of seeing here is this fan has the capability of operating at a lot of different points, but there are certain points it operates at where it's most efficient or minimum efficiency of 1.0. We'll go back here to this is the same fan that I had to use it as an example this entire class. The green dashed line that represents the whole range of capabilities of this one fan, right? Depending on what the static pressure is and what the RPM is, your performance point will land somewhere in this outer green, within the range of that curve. Now, of that same fan we looked at, if I look at just operating points that the FEI is greater than or equal to 1, right? So now I'm circling off. Yes, the fan can do more. It can go higher pressure. It can go faster. It can go more CFM. But all those points of operation of this fan, I'm losing efficiency. I'm dropping. That green circle is all those points that I can pick this fan, and it's at least a 1.0 fan energy index. Now, for our example, I threw that point of operation on here. We're right here. 1.08 is what I use as an example. So I'm pretty happy that I picked a fan operating that can move the right amount of air and is operating in a very efficient spot of its capabilities. All right, last couple of things here. I'm going to wrap up. I just want to look at the effects of a fan curve and really this is the boogeyman, right? This is system effect. Everybody's heard the word. What is system effect? So let's say we have an installation where, the inlet and the outlet doesn't quite look like how it was tested, right? So this is a picture of an inline fan being tested exactly how AMCA, the Air Movement Control Association, told us to test it. A certain amount of straight before and after. This is that perfect laboratory beard net, white coat. This is where we're getting our numbers, right? What happens when the installation doesn't look like a laboratory? You get reality, right? And in that reality, this inline fan looks like this. I'm literally expanding on the inlet, coming down at an angle, and on the outlet, I'm constricting and going up at an angle. That's not how I tested the fan. You changed the inlet and outlet conditions from how it was tested. And because of that change, all this beautiful fan curve information I have been telling you for the last 45 minutes goes out the window. Uh, this fan will operate differently. And I kind of want to really show that on the screen. This red line represents that perfect, operation, how the fan curve was made, right? So I have just a lot of confidence, wherever my static pressure lines up, it crosses that fan curve. That's the amount of air I'm going to move. But when I change the inlet or outlet or both condition from how it was tested, this is what that new curve looks like. I mean, there was no way for me to even imagine that this curve would look like this. So as we move more air or as we have more static pressure, that curve is going to move in a much different spot. Also look at, we brought up hunting, where one static pressure could hit more than one CFM point. Because of the shape of this curve, I have a lot more of those where I could have hunting. The do not operate zone is actually much bigger than the original fan, the way it was tested. So this is a good example of system effect. System effect, I mean, there are different types of system effect. There's system effect out in the system, out in the ductwork, due to filters, dampers, etc. This is the system effect at the fan, and simply defined as a change in the inlet or outlet condition of a fan that affects the efficiency and operation of the motor, right? So I'm going to get a whole different swing on performances, and could operate in a spot that's not healthy for that fan. Oh, and by the way, if I want to take this fan and speed it up, right back to fan laws, I have to speed that fan up. Anytime you speed up or slow down a fan, the existing fan curve is offset parallel, right? So I have a good understanding of where it's going to be. So here's that new operating point with a much faster, louder, and more vibration system. And it's going to use a lot more power to move that amount of air. All right, folks, I did leave some time. Thank you for jumping into this class. Um, I'm going to be quiet here for a moment and we'll see if Terry has some questions.